Okay. So this is the expectation value of any function, a special Hamiltonian. The special, the Hamiltonian expectation value is just replace the Hamiltonian here. Okay. Can I write this expression easier? Yeah, I can write it. So look at that. So what is the expression value of Hamiltonian? We call it this internal energy, no? Before. What is the internal energy? Internal energy is the total energy of the system, no? When you make all the averaging. So I can write it this in more elegant way. So let me just write it. Can I write this minus partial derivative of beta of just exponential with respect to the beta of this integral? So, okay, so ln this. I can write this now. Derivative of ln is the derivative of the function over the function. So if you make the derivative, you get this. So if we be a little bit soft, I mean, derivative doesn't make any change if you put some number here, no? Derivative of the logarithm of some number is 0. So I'm very interested, I put it this h cubic here, from here to here. So what is that? This is the single partition function, single partition function.
Doctor, again, could you repeat this step?
Which?
Minus partial beta.
No, this is, you see that if you take the derivative of this with respect to the beta, Hamiltonian will appear. Exponential, derivative of exponential is the number multiplied with exponential. But I needed this h cubic here to make it this similar to the partition function, so I just put it h cubic here. Because when you take the logarithm of that, it will be logarithm of h. Derivative of logarithm of h is 0 because I think. So and that's all. So if you want to write this, this is the. It seems that this is the expectation value of Hamiltonian for one particular. It seems that because you have a Q. So if you want to write it for Qn, you just needed a little bit modify that. I mean, instead of the Q1 here, instead of the nothing, just here you can write the Qn here. So this equation work even for one particular, for n particular quantities. Just remember that what the h you put it here is singular article, but we always use this Hamiltonian for n particle. So this equation is very important. And what is the ln Qn? You know? No. ln Qn is minus beta helmholtz. Yes. So, one partial beta R. So from this equation you get a lot of interesting information. Like remember that I write you R is U minus TS, huh? R is U minus TS or U plus TS, I don't know. Yes, U minus TS, and you remember that Yeah. This is the U, so even by this way you can find entropy, huh? Yeah, but not necessary to use entropy. If to find entropy from here, you can define from another equation. Anyway, that was very important calculations actually.
Doctor, now U, it is the same as U, that's for expectation value? It's the same U?
Yeah, of course this is the same. The mean of the internal energy is the expectation value of Hamilton. Yeah, it's the same, of course. So U is again I write H, Q and P, E minus beta H, Q and P, take Q. And take a equals Q. So you can make it, you can move all to one side, huh? Because U is number. U is just one number, 3n car t. I calculated for you, it was 3n car pt for the harmonic oscillator. So I can move it all to one side. So write it Q and P minus U. Q. Yes. What is the using this equation? What is the usefulness? So it's not useless, it's useful because I will tell you what will be this. Consider U as a function of the beta. So if you consider U as a function of beta, this actually is, because I told you for simple harmonic oscillator, I mentioned that U is 3n car bt, so was 3n over actual beta. So U is function. If you consider U as a function of beta, what I want to do is that it's a simple calculation for you. Just take the derivative of both sides of these equations and you will get this expression. Consider U as a function of the h and try to make it this simplified. U minus h sub. So this is the first order equation for the U. So what is the useful of this? So if you open the right hand side, so this is just taking the derivative differential and see that you can get this equation or not. If no, we can work on that next time. You can ask me. So I will expand this, okay? I will expand this expression. So when you expand, it's very easy. Partial beta plus. I want to expand that U squared plus H squared minus 2UH 0. U is a number, The average of U is U. Average of U squared is U squared. Just number. So partial beta U squared plus average H squared minus 2u, average h is, what is the average h? U. So partial rho on the u on the e plus u square minus 2u square plus partial h square 0. So I find this average of h square. So let me to be very careful. So this is will be minus u square. Okay, it goes to there. So this is the average of h square. Huh? I want to ask you, maybe think about what is the average of h power n here. But in statistics, in the mathematics, you know why I'm looking for the average of x square just? Variance. Huh? So this is the variance. If you have some numbers, so you have average, you have variance, and you have a higher moment also, like power of variance. I mean the average of x cubed, but you don't need it. You didn't study that before. So higher moments like h3, h4, but for us just h square is enough. So let me to write. So can I write delta h square? The average is just h square minus h square. So will be will be u square minus partial a beta. Now what is this? This is a u. Yes. This is the variance, or they don't write variance in physics. They call it fluctuations. Fluctuations of energy. But the mathematical form is variance, so this is just variance. You don't need to be worried about this partial u with respect to beta, because I don't want to do the last mistake. We spent a lot of time here. Anyway, so just I want to write that again. Use the technique I teach you. Partial beta, change partial beta to partial t by change rule. So you will get kb t square partial t. What is this? You know that is from physics 2, holiday. Change of the energy versus the time is called a heat capacity. Kb t square CAV, YV, any C. So this is heat capacity, anyway. Heat capacity. So heat capacity is the fluctuations of the energy in a gas system. This is the meaning of heat capacity. If you don't have fluctuation, you don't have the heat capacity. So, I don't know, you know about the study of the history of starting the physics, quantum physics, but one of the reasons that quantum physics started was that people find a different form for the heat capacity in the experiment and in theory. And that was one of the motivation for the great people like Planck, and then they started to think about that maybe there is something else about the behavior of, because it was some model for the CV classical models. And when they fit it to the experiment, they find a very huge difference of that, especially when the temperature goes down. So they was thinking that maybe in the low temperature there is something else except the principle which they used before. So, and that was the starting point from quantum physics. So heat capacity is very important and play the essential role to build the quantum theory. And you see that here you have a good more sense about that. So, and you know that the CV for any gas is different. Huh? You can calculate. You need U. So if you have U, for example, for harmonic oscillator, because it's very good for harmonic oscillator, we have already this. So let me just see. Partial U with respect to T is 3n kBt. 3n kb. So will be kV Ts square 3n kV, and this is proportional to Ts square. You know, Ts square was the thing, the CAV which they measured in the experiment. When they plotted the CAV here for the low temperature, here for example, I call it low temperature, the behavior here was like that. Of course you cannot teach, again I told you, you cannot touch the T0, but I mean about the lower temperature. For higher temperature also, it was infinity, yeah, but I don't want to teach. This is the regime of the quantum physics, so, and they were not able to explain that because I think, I'm not sure exactly because I needed to check, but I think the previous calculation showed that at low temperature CAV remain constant or zero. I don't know exactly. But anyway, they are not able to find it, the one which experiment. So this is the experiment and this is the quantum physics. So that was one of the proof for the, and before the quantum physics, so people like Albert Einstein tried to explain this experiment as the difference with the experiment, not using the quantum physics. They tried to use another concept. So you can read it, the history of Einstein. There is a different name for the Einstein models. Yeah, this. So, but anyway, the quantum was the winner. So quantum physics winner. So with this, which is such a strange idea, tried to explain everything. So far, for the atomic system, so we have a very good explanations based on the quantum physics. So that was my important result. So that was I was trying to run to reach to this point. So you can find the fluctuation in entropy, but normally the fluctuation in energy is very important because energy is the one which you can measure. So if you have a distribution of the energy, you remember the accessible state or something like that, and if this is the E, so you can always show that this will be, several times I talked about that, so it will be Gaussian. And any Gaussian will be like that. Hamiltonian. This is the form for Gaussian. If you check at any statistics book, you can see that. Any Gaussian is proportional to the E minus average of the quantity over the variance. So now we get the variance. Variance is KBT CB. So this is the variance. That's the variance. So this is delta H squared actually. And the peak will happen when, so the most probable state for the statistical system is happen when the average energy reach the final value, so final value is internal energy. And when the band of energy is less. So many examples about the, I extended your, so there are many examples about the canonical and some, so maybe later I will send one or two important examples to find the canonical partition function for the system, especially when, for example, one of the systems which you can look at your calculation is that when you have the Hamiltonian of anharmonic oscillator, so